Good morning, George Notchik here. Today is Sunday, the 29th of September, and in this video I'm going to be analyzing a video that is popular amongst people that are interested in gravitational forces of attraction. That is, demonstrating the attractive force that gravity has between two masses, or what we call mass attracting mass. The video that I'm going to be analyzing is very short. I'll be showing it here in a brief moment, but I'm first going to outline what it is. You have a very sensitive weighing scale that can measure down on the order of milligrams. And suspended from this scale is a lead pyramid weight. And you first measure the mass of this pyramid as a gram force. It's actually a force that's being measured, and it's converted into the mass of the pyramid. And first, the weight is measured with respect to the Earth, that the Earth is attracting this mass, and the weight given in gram force is 152.166 grams force. Then they slide a lead ball weight underneath the pyramid to add mass to the Earth that would cause an additional force of attraction. And what you find on the scale after they do that, this last digit changes from a 6 to a 7, showing that the increase in force is increased by 1 milligram force. About a year ago, when I first saw this, it bothered me, but I never really looked at it seriously. I just did some quick calculations and did some head scratching and say, this just doesn't seem right. And I'm going to give you a very detailed analysis and show you that this video is wrong. There isn't any way that that scale should have a digit increase when a mass, that ball mass, is slid underneath that pyramidal weight. Now, to analyze this, we need to first determine the characteristics of this pyramid. That is, its volume and its mass, given its mass, and its dimensions. And from the video, I can determine the mass of the sphere, of the ball that's brought underneath. And I'll show you how I computed that. And in order to analyze this, I had to do some screen grabs, print them out, and then make measurements on the paper. And I'm going to bring you through the steps, the logical steps in which I was able to determine the dimensions of, like, the diameter of the sphere, the side lengths of the pyramid, and from all that, knowing the mass of the pyramid, we can also get the mass of the sphere. So what we start out with, we need to know about the pyramid. Well, the pyramid, I'll be showing you shortly, has a square base. I'm doing it in general here with two different side lengths, and then we'll make them equal. We have a slope length of, call it L, from one of the vertices up to the apex, and then the widths of the base are W1 and W2. Now, we also need to know the height of the pyramid. That's from the center of the base on up to the apex. We'll call that height H. and then going across from the center to one of the apexes on the edge, we'll call that little r for radius. Now, these bases are rectangles, so what we have then is we have this rectangular base where we have square corners, and we have, this is r, this is r, so the diagonal length is 2r. And this is W1, this is W2, and by Pythagoras' theorem, we have 2r squared equals W1 squared plus W2 squared. Now, we can solve for r squared. R squared equals W1 squared plus W2 squared all over 4. Now, the height, if we go, we have a right angle here, so looking at this portion, we have a height, we go out r on the base from the center out to the one of the vertexes, and then we have our height h, and this is a right angle, so we can use Pythagoras' theorem again. So we have L squared, the hypotenuse squared, equals r squared plus h squared. And then we can take r squared in from here and put it in, so we get L squared equals W1 squared plus W2 squared over 4 plus h squared. Now, so we can get the volume of the pyramid. The volume of a pyramid, of a right pyramid like this, is the product of the base lengths of the two sides times the height of the pyramid, that is from the center of the base up to the apex, divided by 3. So we have W1, we have W2. We can solve for h in this equation and put it in, and then we'll have the volume in terms of the side lengths. And if we do that, the volume of the pyramid works out to W1 times W2 over 3 times L times 1 minus W1 squared plus W2 squared over 4 L squared and the square root of that. Now, if we have a square base, W1 equals W2. So we have a square base, so W1 and W2 are equal and is equal to W, and if you put that in, W1 and W2 are each W, and the same there. This will then work out to the volume is W squared L over 3 times 1 minus W squared over 2L squared to the 1/2 power, or the square root. And you can see that if W1 and W2 become W, so we end up with 2W squared. The 2 cancels with the 4, so we end up with W squared over 2L squared. That's what we have there. 1 minus that to the 1/2. Then W1 times W2 becomes W squared, and then we have L over 3. Now, we can work this out in that I'm going to group terms here in the following manner. We have the volume is equal. I'm going to divide by L squared in the denominator, multiply by L squared in the numerator. So I'll have L squared, L cubed, and then I can group this as W over L squared L cubed over 3 and that's times 1 minus 1/2 W over L squared to the 1/2. And I'm going to establish a factor K, which is the ratio of the width to the length on the side, on the pyramid. Is we have this base that's square, we have a square base, and then we have a side length of L, and the K is the ratio of the width or the length of a side on the base to the slope side on the pyramid. Now, if we do that, we can express in terms of K, so our volume then becomes K squared L cubed over 3 times 1 minus K squared over 2 to the 1/2. So this is our equation for the volume of the square base pyramid. Now I'm going to do one other thing here, is if we look at one of the faces, let's take the front face. The front face is going to look like this. The slope side is length L, the base is W, and then we have an angle theta that the edges of the face make. Now, by using the law of cosines, we can get a relationship. That is, W squared is equal to the product of the sum of the two side lengths squared. So we have 2L squared minus twice the product times the cosine of the angle between them. So W squared equals 2L squared times 1 minus cosine theta. Well, I can very accurately determine what theta is, as well as the side lengths, and I prefer to work with the angles. Now, so we can see here then that W over L squared is equal to 2 times 1 minus the cosine of theta. Well, W over L is our K, so this is K squared. So we can get K in terms of the angle that the two sides make. So our volume then, in terms of theta, becomes W over L squared here, which is our K squared. And then we also have this K value here. So we can write this as our K squared is 2 times 1 minus the cosine of theta. That's this K squared here. L cubed all over 3 times 1 minus K squared over 2. Well, let's look at what that value would be. So if we take K squared over 2, we bring our 2 down here. The 2 disappears. I'm going to get rid of that there. And then, if we subtract this from 1 and bring the cosine over, we can write this now as 1 minus K squared over 2, bringing that over, and then the cosine over here is equal to the cosine of theta. Well, look at, we have 1 minus k squared over 2. So this just becomes the cosine of theta. So there's our volume to the 1/2 power. Okay, we're taking the square root of this quantity. So there is another expression for our volume. If we know the angle and we know a side length on the slope, then we can compute the volume using this particular equation. And then also we have a relationship, you can work this out, is that the height is L times 1 minus k squared over 2, which is L times the cosine of theta. And we can see that is the height is just going to be that's to the 1/2, I'm sorry. It's the square root of 1 minus k squared, so that's L times cosine to the 1/2. So there's our expressions. These what we'll be using. So I'll rewrite this because I'm going to be using this. So I'm going to write that the volume of the pyramid is 2/3 times 1 minus the cosine of theta times the cosine of 1/2 of theta, and this is times L cubed. So 2/3. So that's the volume of the pyramid. Okay, that's this expression here, 2/3 L cubed 1 minus cosine theta times the square root of cosine theta. Okay, so that's for our square base pyramid. Okay, now I'm going to go ahead and play the video, and then we'll get back and analyze the video now that we have our expression for the volume of the pyramid.
First, we weigh a small lead pyramid to measure the force of attraction between it and the Earth. Its weight is 152.166 grams. Now we move the heavy lead ball under the scale, adding its mass to the mass of the Earth. The weight is increased by 1/1000th of a gram, which represents the attraction between the pyramid and the ball. When the mass under the pyramid got bigger, the force of attraction did too.
Here I have a screenshot that I put together, three screenshots at 3 different times. The times don't correspond to the video that I'm linking. I had access to the original video that the video that I just showed you is extracted from. But what we have here are different views of the pyramid and of the ball that was moved underneath the pyramid. And these numbers, these dimensions in millimeters, is what I've measured on the paper. I've done a screenshot and I've done a very accurate measurement. Now, these measurements do not correspond, are not the same as the physical measurement of the pyramid and the ball. They are the measurements on the paper. We are not given the actual dimensions, but we can determine it, what the actual dimensions are, because we know the mass of the pyramid. And given the expression for the volume and knowing the density of lead that the pyramid is made of and the ball are made of, we can get the actual dimensions. We can get L if we know what theta is and we know what the volume is. We can compute the volume from knowing the mass, and I'll show you that in a moment. But first, we want to determine what theta is, and I've measured it in two different screenshots to be 39 degrees. So the angle from the apex on down, slopes on the side, are 39 degrees. Now, the way I got that is by using the law of cosines. I've measured the side length. Now again, this isn't the actual physical dimension. The slope L in my picture is 53.5 millimeters. And the width, or the base width, is 35.5 millimeters. So we can get the ratio of L to W, which is 53.5 over 35.5. All we care about are the ratios, and that is 1.507. Well, from the law of cosines that we computed, we know that W over L squared is 2 times 1 minus the cosine of theta. So we know W over L, and we can solve for the cosine of theta. The cosine of theta, if I put in the numbers, works out to 0.7798, which gives us an angle of 38.75 degrees. So I'm using 39 degrees. Now, also from the dimensions on the paper, I have the diameter of the sphere, we'll call it big D, is 50.5 millimeters. So we can now get the ratio of the diameter of the sphere to the side length on the pyramid. I'll show you that in the next diagram here. So here's another screenshot where there was a close-up of the pyramid and the sphere. So I completed the sphere, and I measured the diameter in millimeters in this particular view, and the D was 166.0 millimeters. But also in this same photograph, L is 70.0 millimeters. So we can get the ratio of D to L. So D to L is 166 divided by 70, and that works out to 2.371. So that's our ratio of the diameter of the sphere to the side length on the pyramid. So we have our angle theta, we have the ratio of D to L, and now we can compute the actual dimensions from these. Now, one other thing, before I do that, I'll show you yet one more screen grab, and that's this one, to get what the separation distance is between the bottom of the pyramid and the top of the sphere. Is in this particular screen grab, the diameter of the sphere is 46.5, the gap is 1.5 millimeters. So the ratio then, I call this dimension, the separation S, that's 1.5 millimeters. The diameter of the sphere is 46.5, so S to D is 1 over 31. So the gap the separation distance is d over 31. I'm now going to show you why I believe the base to be square rather than triangular. If we look at this shot of the pyramid, we see that there's a vertex line between two faces right here where I have the red line drawn. So we have a little bit of left face here and almost a direct frontal face on showing in this area. So the way that the angles are, I cannot see that there would be just a single face behind here. There's going to be two faces. There'll be one slanted in off this edge and then another one connecting to this edge here. And we can see that with this particular shot is, again, we have two faces. We're looking direct on. It's divided right in half. We have the lighter face here, side 2. We have the left side here. This is direct on. So on the back side, we would expect to see exactly the same sort of symmetry. So I'm quite confident that the base is square. I have now moved all the important equations off to the right hand side here. Here we have the volume of the pyramid given in terms of theta and the slope length. Here's our angle, theta, that we just measured for the pyramid, 39 degrees. The ratio of the sphere diameter to the slope length on the pyramid is 2.371. The gap length in terms of the sphere diameter is the diameter of the sphere divided by 31. Our K value is W over L, which is 1 over 1.507. Our K squared, this can be written in terms of cosine in this manner, and then the pyramid height from the center of the base up to the apex is L times 1/2 of the cosine of theta. And I've also included here, this is the volume of the sphere. It's pi over 6 times the diameter cubed, or most of the time we find it written as 4/3 pi r cubed. But if we put in for r d over 2, then we've got d cubed over 8. 4 goes into 8 twice, so that's where we end up with the 6. Now, let's go ahead now and determine the actual dimensions on the sphere and the pyramid. We know that the pyramid mass, that's a given. We know that from the video. The pyramid mass, I'll call it MP, is 152.166 grams. Now, we know that the pyramid is made out of lead. That's we're given. So the density of lead is 11.34 grams per cubic centimeter. The relationship is density is mass per unit volume. Well, we know the density, we know the mass, we can solve for volume. So the volume of the pyramid then will be the mass of the pyramid divided by the density of lead. Right, that is PB. So we have 152.166 grams divided by 11.34 grams per cubic centimeter. So now we've got our our volume. 152 divided by 11.34 comes to 13.42 centimeters cubed. So that's the volume of our pyramid. Now, from this equation then, we can get L, because we now know the volume of the pyramid. We know theta, so the only thing left is L cubed. So putting in the numbers here, so we have the volume of the pyramid, then putting in for theta in this equation, we end up with L cubed over 7.635. But we know the volume of the pyramid. This is 13.42 centimeters cubed. We can cross multiply, so L cubed then is 13.42 times 7.635. So L cubed then is 102.45 centimeters cubed. Take the cube root of each side, so L then is 4.68 centimeters. So that's our L. That's the slope side length on the pyramid. If we look at the pyramid face, we have an angle of 39 degrees. This length is L. So we know this is 4.68 centimeters. That's that slope length. Now, knowing the cosine of theta and knowing L, we can get our height. The height of the pyramid works out to 4.134 centimeters. That's our height H. And then the base, by knowing L, we can solve for the width, or the base length is just L over 1.507. So W then works out to this length here on the base is 3.10 centimeters. That is 4.68 divided by 1.5, or roughly 0.6. 0.6 times 4.68. Now, we need to know one other thing for the pyramid, and that's its center of mass. I'm not going to compute that out. I'm just going to give you that number. So we have, now, we don't need any of this. We don't need to know the volume of the pyramid anymore. All we need to know is L. So L is 4.68 centimeters. Now, if you have a pyramid with a square base, it turns out that the center of mass is 1/4 of the height. So it's H over 4 from the base up. Now, with this computation here, our H then works out to 4.134 centimeters. So H over 4, which is the center of mass up from the base, is 4 into that, which is 1.034 centimeters. So these are the actual dimensions. Now, from this, we can now get our sphere dimensions. Remember that the sphere diameter is related to L. We know L. So D is just 2.371 times L. So the sphere diameter is 2.371 times L, which is 4.68. So the diameter then is 11.1 centimeters. 2.371 times 4.68 centimeters. So that's our sphere diameter. The volume of the sphere then is given by pi over 6d cubed. So we have pi over 6 times d, 11.1 cubed. So the volume of our sphere is 716.1 cubic centimeters. Now, the sphere is also made of lead. Lead has a density, again, of 11.34 grams per cubic centimeter. We know the volume of the sphere, so we can get the mass of the sphere. So the mass of the sphere is the density of lead, Pb, times the volume of the sphere. So we have 11.34 times 716.1 cubic centimeters. So the mass of the sphere comes out to 8,120 grams. Now, one last thing is we have to get our separation gap. The separation is d over 31. So S is d over 31. D is 11.1 divided by 31. And this works out to 0.36 centimeters. So now we can compute the force, the gravitational force of attraction between the pyramid and the sphere that's moved underneath it. That's how much the scale should indicate in terms of that additional force of attraction. That will cause the scale to change. So let's work that out. I'll just let you take a look at that before I erase the right-hand side. And let's see, I'm going to move these to give me a little more working room. So I'll rewrite these numbers. So we have our L, we have our height, we've got our W, which was 3.10 centimeters. We've got the, now for the sphere, we have the diameter of the sphere, cap D. The diameter is 11.1 centimeters. The volume of the sphere is 716.1 cubic centimeters. The mass of the sphere is 8,120 grams. The separation between the base of the pyramid and the surface of the sphere is 0.36 centimeters. Okay, so now let's compute the force of attraction. We have our sphere and our pyramid. We've moved our sphere. I'm exaggerating the gap here. So to compute the force of attraction from Newton's force law, we have force is big G times the mass of the sphere times the mass of the pyramid over the separation distance squared between the centers of mass. The center of mass of the sphere is at the center. So the distance from the center to the surface is just cap D over 2, which is the radius. I'll call it big R. Then we have our separation distance, and then we have h over 4. That is from the base up to the center of mass of the pyramid. So our R, our little r here, is going to be the sum of these three things. It's going to be the radius of the sphere plus S plus h over 4. So we put our numbers in. Radius of the sphere is d over 2. So 11.1 divided by d over 2 is 5.55 centimeters. Plus S is 0.36 centimeters, and h over 4, h divided by 4 here was 1.034. So then we add 1.034. So this works out to R, then the sum of those three numbers is 6.94 centimeters. So that's the distance between the centers of mass of the pyramid and the sphere. That's 6.94 centimeters. So in using this equation, G is 6.674 times 10 to the minus 11th. And then the mass of the sphere, the masses have to be put in kilograms. So the mass of the sphere is 8.12 kilograms. And then the mass of the pyramid in kilograms is 0.152. 17, we'll call it. And then R squared, R has to be in meters. So this is 0.0694 squared. Now, when we compute that, this works out to, the force is 1.763 times 10 to the minus 8 newtons. That is the force of gravitational attraction between the pyramid and the sphere. Now let's look at how that compares with what the scale is indicating. I'm going to get rid of this stuff here, so we'll just let you take a look at that. Okay, now, the scale, remember, indicated 1 milligram force, 1,000th of a gram. Well, what is that in terms of newtons? Well, 1 gram of force, 1 gram force is 9.80665 meters per second squared times the mass in kilograms. The gram, 1 gram is 10 to the minus 3rd kilograms. So 1 gram force is 9.80, let's round it to 7, times 10 to the minus 3rd newtons. But this is, the scale indicates 1,000th of a gram, so it's 1,000th less than this. So 1 milligram force is 9.807 times 10 to the minus 6 newtons. That's the force change that the scale is indicating. When it changed the last digit from a 6 to a 7, it is telling us that the force being registered is this. Compare it to what it ought to be for given the masses of the pyramid and the sphere. There isn't any way that that scale could indicate this force. This force is considerably smaller than 1 gram force that scale is indicating. How much smaller is it? Well, if we ratio these two, if we divide the actual force between the two masses into the 1 milligram force, that ratio comes out to, let's call it the force of the scale indicated to the force actual, and that is a ratio of 556 to 1. We're off by more than 2 orders of magnitude on that scale. there isn't any way that the scale could possibly indicate a force change when that sphere is brought underneath the pyramid. Now, another way we can check this is if we assume, we could go ahead and assume, just for a quick calculation, suppose we take the sphere and we put all of the mass of the pyramid resting right on the surface of the sphere. Let's say it doesn't have any dimensions. It's a point source. So it's 0.156 kilograms sitting on the sphere, and then we use the radius of the sphere to calculate the force of attraction. So in this case, the force is going to increase because that mass of the pyramid is brought in closer to the surface of the sphere, or to the center of mass of the sphere. And if we calculate that out, rather than 0.0694, what we would be using is, for our radius, it would be 0.0555 squared. So it's a smaller number, so the force is going to go up accordingly. And in this case, the force would work out to 2.68 times 10 to the minus 8 newtons. And if we compare that to 1 milligram of force, that ratio then drops to 366 to 1. Still way off by over 2 orders of magnitude. So there isn't any way that that scale could possibly indicate a force change. It's not enough force to be measured with the scale. So we have to ask ourselves, what's going on here? Why is there a change on the scale? Well, I have a couple ideas on that, given that my whole career has been based on instrumentation, precision instrumentation, and I'll give you some educated guesses as to what might be going on. Now, in any instrumentation, whether it be analog or digital, has limitations as far as linearity goes. That I am always suspect. I never would ever trust a measurement that is registering just a single count or a single digit change in its resolution. In this case, the scale is reading 152.166, and then the 6 jumps up to a 7. You cannot trust the last digit of resolution in any instrumentation. I have never seen any instruments where that last digit is accurate. It's just impossible to do because of noise, because of linearity. In the case of a digital piece of equipment, you have an A to D converter. The A to D converters can only be made linear over a certain range. And the same thing with any analog scale. If you have like a spring has a range of linearity. If you have a spring, we have force equals kx, where if we start stretching the spring out from its equilibrium position and go a distance x, this would be x equals 0, and we're stretching that spring out, then the force that the spring exerts in trying to pull back is linearly related to the distance that you stretch the spring to within limits. You could end up really stretching this thing out to where you distort the spring and it won't go back. You get into a nonlinear range. So there's just a range of distances that you can stretch a spring out and have this linear relationship hold. Now, my guess that might be happening on this scale is this scale may have been just on the edge of changing. It was on a boundary between the two digits, between the 6 and the 7, so that a minute little force would flip it. So on that scale, with the indicator being on the boundary where a little force might flip it, could cause that to happen, or there might have been some noise in the system that can help push it over when that additional force of attraction was brought in. Even though it's on the order of 1/500th, it might have been just enough to flip that digit. The other thing that could be going on is, as you have this pyramid and you slide the spherical mass under it, there could have been maybe some electrostatic type forces if these weren't properly grounded or shielded. So say if there's some excess positive charge on the pyramid, and with the sphere ball in contact with the earth, might have a negative charge with respect to the pyramid, which would cause a force of attraction between the two, that if that digits on the scale was right at the boundary, it could flip it to a 7. That's a possibility. I don't think it's particularly likely, but you never know. So my guess is that the scale was on a boundary being ready to flip anyway, and just adding a little additional force caused it to flip. And this goes to show that why it's so difficult to repeat the Cavendish experiment. As amateurs at home, you're never going to be able to do it. In this particular case, the force of attraction that we just calculated was on the order of 10 to the minus 8 newtons. That's newtons. That's 100 millionth of a newton. That's extremely small. That's on the order of 1/10 millionth of a gram. A millionth of a gram. So this scale can only measure a milligram. It would have to have a resolution down in here, 3 more digits, before it would be able to register or indicate a change as this lead ball was brought underneath the pyramid. So this is way beyond the capability, measurement capability of that scale. Now the way that you can do this, of course, is the way Cavendish did it. Is you have a beam that's suspended from a torsion wire, and you have some masses on the end of this torsion bar, and then you introduce a weight, and it causes this to rotate. And by knowing the torsion constant of this wire, you could compute what the forces are to cause it. It's much easier to cause things to rotate that's suspended by a wire than to do anything with a scale. Now, you're able to do this in physics classes, at least qualitatively, not quantitatively, but at least you could bring a mass in and show that it's causing a movement that causes this thing to rotate. If we look at this from top down, we have our suspension wire here, and we have our masses, and then what we do is we introduce a mass here and a mass here. That causes a torque on this end that way and a torque on this way, so you get double the force, effective force, that's going to cause this thing to rotate around. So you can indicate, at least qualitatively, that something is happening with the forces, but you have to go to great care and great pains, like Cavendish did, to have the thing shielded in a room so you don't have air currents. You have to be away, look at it with a microscope so the mass of your body isn't influencing the outcome of the experiment. So amateurs that are building these things at home don't have a prayer of making this work. Because the forces are so small. You're trying to get, with these types of masses, of 1/100th of a millionth of a newton. Now, you could build these things with, say, larger weights, where you might have, say, 50 kilograms on each and bring 50 kilogram weights in, and you can probably get this down to about trying to measure 10 to the minus 6 newtons, but that is still a very, very small force. So you're kidding yourself if you think you're building this apparatus at home, because it really takes a lot of precision and care to build a Cavendish type experiment test apparatus that's going to indicate these force changes or mass attracting mass. You can maybe demonstrate it qualitatively, but you'll never be able to calculate what big G is, because you just can't, without great precision, design something that can actually qualitatively or quantitatively, where you can actually make analytic measurements of the force to know what the forces are, so you can calculate big G. So anyway, I find this video very disturbing. I don't know what went on there. They should have taken some care to do some calculations to see if it made sense what the scale was indicating, but this happens. I see this a lot on videos put up on the YouTube, even by people that should know better. So there you have it.